This is chapter 8, question 1. It gives you the shell, and that's also going to be referred to as the energy level and equals. So the n is our principal quantum number, and given n, you get the angular momentum quantum number, L. L is always going to be n minus 1. So when you get, oh my gosh, when you get n is equal to the energy level 1, the L will be 0. And using this table, you can get when the L is equal to 0, you have an S subshell. When when L is equal to 1, then you'll have a P subshell, and so forth. So given, let's say, this shell being 2, you know that you will have n equals to 2. That means the L is equal to 1. And when you get the angular momentum quantum number, it'll be 1 also starting from 0. And for another example, let's say n is equal to 4, L is equal to 4 minus 1, which is 3. So you get all of the angular momentum quantum numbers up till 3. So you get 0, 1, 2, 3. And the code that they show you here, there, is S being 0, P being 1, 2 being B, and then 3 being F. And then you can just write all of that in the subshell that they show you for S, for P, for D, for F. And some other information that is good to know is that the N is also going to be given by your period. So at this first row, we have n equals to 1 for all of these elements. And then it'll be n equals 2 for all of these elements as well. And we also see the subshells shown here. So when we have 1 or 2, that's going to be this first subshell. And then we go to the third electron right here. And we're going to know that it's going to go to that 2,2s subshell. And then when we have our boron with the 5 electrons, we just count 1, 2, 3, 4, 5, and then it's going to be that p subshell. Another thing to know, for the most part, as you go to the right, you're just adding electrons, and you can see through this periodic table that we're just adding electrons as we go side to side, and we're just going up a n level, a energy level. And one thing to note is that at that fourth element, we're going to go from 4s to 3d, and then we go to 4p, and then we basically continue so forth. And just know that as you get to the sixth one, you have to go down, and then you have to include these into 4f. And then let's see, you just continue back to the periodic table. And finally, you can also look at this diagram. You basically go through the first subshell, 1s, and that takes 2 electrons denoted by that top right number. Then you go to 2s, then you go to 2p, 3s, 3p, 4s. And then another diagram is this one. We see that 1s goes here, and then 2s, and then 2p, 3s, 3p, and then 4f, 5f is at the bottom. But the 4f, 5f are more complicated, and we probably don't need to know that. So we know what n level is like say 3, then we know that the angular quantum number is going to be n minus 1. So we have the possible subshells being 0, 1, 2, and we know it's S, P, D. From there, know that the S subshell can only hold 2 electrons, P can only hold 6, and D can only hold 10. 3s, 3p, 3d. So the angular quantum number is giving us our suborbitals, and our suborbitals will give us our magnetic quantum number. Oops. Magnetic quantum number tells us what's excuse me. So our angular quantum number gives us our orbital, so that's the sp or d, and then the orbital will give us our magnetic quantum number, which is ml, which is the positioning of where the electron is going to be. So for example, for S, the magnetic quantum number will always be 0. And that's denoted by just having that one block that the electrons can exist in. But for P, for example, there's 3 magnetic quantum numbers. And that is -1 here, 0 here, and 1 here. And so the magnetic quantum number will basically be for, let's say an electron is ending up with, an electron ends up with 5 electrons total. So it'll fill up first that 1s, then that 2s, then that 2p, and it'll land on that first suborbital. And that's going to be denoted by -1 because that's that first one. Let's say it landed on the 6th suborbital, that'll be 0. Then let's say nitrogen, which has 7 electrons, is going to end up with that third suborbital, which is going to be denoted by 1. So then let's say the question is, what is the magnetic quantum number of nitrogen? You're going to put what? And for that final quantum number, magnetic spin, basically when the arrow is up, it's going to be +1/2. And then when the arrow is negative, it'll be -1/2. So let's say, what is the magnetic quantum number for oxygen? You can see there that its final electron is pointing down. So the answer would be, for the magnetic spin quantum number of oxygen, it will be -1/2. Just know that as you fill those suborbitals, you want to go fill them up one at a time. So you don't put 2 in the same suborbital until that shell is complete. Actually, ignore shell. A better word is block. So put 1 electron per suborbital at a time, and then once each of those suborbitals have only 1 filled, then you can put the second one in. Y'all know what I mean. All right, so this is basically what I talked about, and then this is number 2, by the way. And then the maximum number of electrons for the 4D subshell. You can see here that there's 5 suborbitals with 2 electrons filling each suborbital. So then the total possible amount of electrons that can go in there will be 10. This question asks you, this is question 3, asks you to order the electron subshells in increasing order. So you basically do n plus the angular quantum number. So let's say 2s, so n is equal to 2, and then s is equal to s being 0. So 2 plus 0, that's going to be the energy. And then 2p that's gonna be your final answer is gonna be 3 for the energy, and then 3D is going to be 5. And then we know that 3D is going to be the highest energy then because the final answer being 5, and then you kind of just do your math that way. Another way to look at it is through the periodic table. So basically, as you go along the periodic table, you see that we're filling up those suborbitals. Um, you can basically go from 3p here to 4s, and then here you go to 3d. So some people might think that 3d has less energy than 4s because of the n energy level, but that's not true. Even though 3d has a lower n quantum number than 4s, it actually has higher energy. So that's just something to keep in mind. And then you also can look at this. This is basically showing you how like the electron suborbitals get filled up. And so that way you don't have to memorize anything to know like how the subshells the how to know the subshells order. You basically just remember 1s, and then you do the n equals 1 plus the quantum number is going to be s is going to be, what is that? Actually, as I know, I think what to memorize is knowing that there is a single 1s block there, and then there's a 2s here, there's a 2p here, there's a 3s, 3p, 4s, then the d block. You kind of just want to memorize like the sections of the d block and the p block and whatnot. Um, oops. Okay. So I watched this video on how to memorize the electron configuration, which is basically the order from 1s, 2s to 2p, 3s, 3d, like how it goes. So you can watch that video. I'll send it on there, or you can kind of try to memorize it another way on your own, I guess. This is question 4. So you're asked to find the elements electron configuration, and they want you to use the noble gas core. So you basically look to that previous noble gas and you see that it's AR. What that means is like you see here, AR has 18 electrons. So because you don't want to write the entire thing, you don't want to go from 1s to 2s to all that, you're just going to write that noble gas core, and that's going to take the place of all of those 18 electrons that you don't want to write. So from there, you go to, let's say, that 19th electron. You know that it's going to start at 4s, as you see in that diagram. And then you go to fill out that 4s. You're now going to go to 3d. And then you only need 2 electrons to fill 3d, because if you subtract let's see. If you know that from AR has 18 electrons, and then you see that like that green block is 4 spaces to the right, that means there's just 4 more electrons from there. So you can see that there's just 4 electrons in that electron configuration. So that's another way to kind of know that you did it right. They also write it from the highest energy level. So you can see that 3D goes first, and then 4S, which is that lower energy level, goes second. This question talks about the size of atoms. Basically, as you go to the right of a periodic table, the effective nuclear charge will increase, which means that the nucleus will hold the electrons closer because the charge between the neutrons, sorry, the charge between the protons and the electrons um are holding each other more tight together. And then because they're holding so tightly comparatively, um that makes the atom smaller because the electrons are being confined versus if the charge was holding those electrons looser, then that atom would be able to be bigger. Another thing to know is that as you go down the periodic table, that means that the atoms also get bigger because you're adding more electrons, one, and two, actually, the most important reason that the reason the size increases is because you're adding shells. So remember n equals 1 to blah blah blah. You're basically increasing the size that way. And also know like anions, you're adding an electron to something, so that makes it bigger. Cation, you're taking away, so you're making it smaller. You can also know that as you go down the periodic table, because there's more electrons in the lower shells, those block the outer electrons, the valence electrons as well, which allows them to get further away from the nucleus, which allows them to be bigger.